While billion-dollar manufacturers replaced equipment every decade, a forgotten 1906 Foundry machine sat in a Pennsylvania basement running 24/7 for 118 years without a single mechanical failure. And when engineers finally opened it up, what they found inside rewrote everything we thought we knew about industrial longevity. December 2024, Bethlehem, Pennsylvania. Michael Torres pushed through the basement door of the abandoned Lehigh Iron Works, his flashlight cutting through decades of accumulated dust. The structural engineer had been hired to assess the building for demolition, but the rhythmic hum vibrating through the concrete floor stopped him cold. Something down here was still running. The machine sat in the corner like a mechanical dinosaur, a Patterson Sons compressed air pump, its brass nameplate green with patina but still legible. Manufactured 1906, Philadelphia. The flywheel rotated with hypnotic steadiness, driving twin pistons that compressed air into holding. Tanks feeding pneumatic tools throughout the long dead factory. Torres checked his instruments. The machine was operating at design pressure, maintaining 120 psi with variations of less than 2 psi. It had been running continuously since Teddy Roosevelt was president. The discovery triggered a cascade of disbelief through engineering circles. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. Patterson Sons had vanished from business records in 1932, absorbed during the Great Depression by conglomerates that themselves no longer existed. No maintenance logs existed, no service records, no replacement parts orders. The machine had simply been installed, started, and forgotten, running through 2 world wars, the space age, the computer revolution, and the birth of the internet without human intervention. Dr. Sarah Chen from MIT's Department of Mechanical Engineering arrived 3 days later with a team of graduate students and enough diagnostic equipment to fill a van. This violates every principle of modern reliability. Engineering, she muttered, running her hands along the machine's cast frame. Nothing runs for 118 years without maintenance. Nothing. But the evidence hummed steadily at 180 RPM, indifferent to her skepticism. The machine's original leather drive belts had petrified into a material harder than the oak they wrapped around, yet still transmitted power with 94% efficiency. The main crankshaft bearings showed wear patterns measured in hundredths of a millimeter after 1.03 billion revolutions. The cylinder walls retained crosshatch patterns from their original honing, visible under magnification despite a century of continuous operation. Torres pulled the building's electrical records. The machine drew 73 kilowatts continuously. Electricity costs that had been automatically drafted from a trust fund established by the factory's original owner in 1908. The fund still held $127,000, enough to power the machine for another 40 years at current rates. Someone in 1906 had planned for a century of operation and funded it in advance, as if they knew their creation would outlast their company, their industry, and possibly their civilization. The question that kept Chen awake that first night wasn't how the machine still ran. It was why everyone who came after had forgotten how to build things that lasted. James Patterson had learned ironwork in the shipyards of Glasgow before emigrating to Philadelphia in 1883, carrying with him a conviction that would define his life's work. Machinery should outlive its makers. His apprenticeship under Scottish marine engineers had instilled the principles that seemed almost religious in their devotion. Build for the worst conditions imaginable, then double every safety margin. The philosophy manifested in Patterson's Foundry with practices that made financial analysts shake their heads. Where competitors cast pump housings in standard gray iron 3/4 inch thick, Patterson specified mehanite iron at 2 1/4 inches. When purchasing agents questioned the 300% material cost increase, his response became company legend. "I'm not building for next year's balance sheet, I'm building for next century's engineers." Patterson's design notebooks, discovered in the Pennsylvania Historical Society archives by Chen's research team, revealed systematic thinking that bordered on obsessive. Each component underwent failure mode analysis decades before that term entered engineering vocabulary. Bearings were sized not for expected loads, but for worst-case scenarios that included seismic events, flooding, and operator malice, Patterson's term for deliberate sabotage. The compressed air pump that Torres discovered embodied these principles in every detail. Its crankshaft was machined from a solid billet of nickel-chrome steel that weighed 340 pounds before machining and 280 pounds after, the removed material representing Patterson's refusal to compromise. The connecting rods used bronze bushings sized at 3 times the calculated load capacity, with oil grooves hand-chiseled by craftsmen who spent entire days on components other manufacturers stamped out in minutes. But Patterson's genius extended beyond over-engineering. He understood that longevity required more than strength. It demanded systems thinking about failure cascades. The pump's lubrication system operated on pure gravity feed from an overhead reservoir, eliminating dependence on pumps, seals, or moving parts that could fail. Oil flowed continuously through channels machined into bearing surfaces, creating pressurized films that prevented metal-to-metal contact under any operating condition. The reservoir itself demonstrated Patterson's foresight. Cast as an integral part of the machine's frame, it held 45 gallons of lubricant, enough to feed the bearings for 6 months even if never refilled. Sight glasses on 3 sides allowed visual inspection without tools, and the fill port accepted any oil with viscosity above 150 SUS, eliminating dependence on proprietary fluids. Patterson's company produced only 347 machines before the Depression forced closure in 1932. Most were scrapped during World War II. Metal drives, their extraordinary construction making them attractive sources of high-grade steel. Chen's research team located 12 survivors worldwide, and every single one still functioned. The average operating time, 97 years, the shortest, 73 years. One machine in Auckland, New Zealand, had pumped water continuously since 1909 through earthquakes that leveled surrounding buildings, still running, still reliable, still ignored by modern engineering textbooks. Chen's team began disassembly on January 15, 2025, documenting every step with 4K video and photogrammetry that would create digital twins accurate to 0.01 inches. The machine came apart reluctantly, its bolts requiring penetrating oil and careful heat application to break threads that had remained undisturbed since installation. No thread damage, no stripped fasteners, just perfect engagement after 118 years of thermal cycling. The main bearing inspection revealed results that made Chen call her department chair at 2 a.m. Under microscopy, the bronze bearing surfaces showed wear depth of 0.014 inches, barely measurable after a century of continuous operation. The secret lay in Patterson's surface preparation. Instead of standard machining, the bearings had been hand-scraped by Scottish craftsmen using techniques inherited from Whitworth and Maudslay, creating microscopic oil pockets every 0.021 inches that functioned as permanent lubrication reservoirs. Graduate student David Kim discovered the next surprise when analyzing the piston rings. They measured 0.127 inches thick, nearly triple the dimension modern engines used. Patterson had recognized that ring wear rate remained constant regardless of thickness, so tripling the material meant tripling the service life. The rings showed 0.41 inches of wear on their inner surfaces, leaving 0.086 inches of serviceable material remaining. Extrapolating the wear rate suggested another 120 years of operation before replacement became necessary. The cylinder walls told an even more remarkable story. Patterson's team had honed them using techniques that wouldn't be understood scientifically until the 1960s. The crosshatch pattern, still visible under magnification, held angles precisely calculated to retain oil films while allowing gases to seal effectively. Modern tribology research called it plateau honing. Patterson's machinists had simply called it proper finishing. Chen focused her attention on the machine's most critical component, the crankshaft. Forged from a steel alloy containing 3.5% nickel and 0.8% chromium, it represented metallurgy more advanced than contemporary automotive practice. The composition provided toughness and fatigue resistance that exceeded specifications for materials not invented until the 1940s. Patterson had somehow identified the ideal alloy through empirical testing, arriving at conclusions that required 40 years of scientific research to validate. The flywheel inspection provided the final revelation. Weighing 890 pounds, it was 6 times heavier than calculations suggested necessary. But Patterson wasn't engineering for minimum requirements. He was engineering for perpetual motion. The massive flywheel smoothed power delivery so effectively that the machine produced almost no vibration, eliminating the fatigue stresses that destroyed lighter equipment. Accelerometer readings showed vibration amplitudes of 0.003 inches at the frame mounting points, barely above background noise, approaching the theoretical limits of mechanical smoothness. Every component revealed the same pattern, deliberate over-design combined with manufacturing precision that modern shops struggled to replicate even with CNC equipment and computer-aided design. The financial records Chen's team uncovered from Patterson Sons told a story that explained why the company's approach had died with its founder. Each compressed air pump required 1,840 hours of direct labor, nearly a full work year per machine. Competitor products reached market in 240 hours. Patterson's material costs ran 340% above industry standards. His machines sold for $4,200 in 1906 dollars, while comparable equipment listed at $950. Thomas Brightwell, a business historian from Wharton, analyzed Patterson's financial statements with growing disbelief. The company lost money on every unit sold, he explained to Chen's team during their research collaboration. Patterson was subsidizing the true manufacturing cost from his personal fortune, essentially paying customers to accept superior products they didn't want. The market's rejection of Patterson's machines wasn't about performance. Customers acknowledged their superiority in every measurable category. The problem was philosophical. Industrial purchasing agents in 1906 were beginning to embrace a new concept called capital turnover efficiency, imported from German economic theory. Better to buy cheaper equipment that could be replaced every 20 years as technology advanced than to invest in expensive machines that would outlast their operational context. Patterson's sales ledgers revealed the painful consequences. Annual production peaked at 47 machines in 1911, then declined steadily as competitors introduced lighter, faster, cheaper alternatives. By 1925, Patterson was building only 8 machines yearly, each one a financial loss leader that demonstrated his principles to an increasingly indifferent market. The company's final machine shipped in January 1931 to a textile mill in North Carolina. It still operates today, pumping air for a facility that's changed ownership 7 times. But the economic analysis concealed a deeper truth that Torres recognized while studying the Lehigh installation. Calculate the total cost of ownership over a century, he suggested to Chen's team. They built the model with contemporary data. The Patterson machine cost $4,200 in 1906, equivalent to $137,000 today. 0 maintenance costs, 0 replacement costs, operating cost of $7.30 per day for electricity. Total 118-year ownership cost, $450,000. The comparison equipment told a different story. 7 replacement machines over 118 years at an average cost of $45,000 each, $315,000. Maintenance contracts averaging $12,000 annually, $1,416,000. Downtime costs from failures and replacements, $340,000. Total cost, $2,071,000. The Patterson machine delivered the same air compression service for 22% of the life cycle cost, but only if owners thought in centuries instead of quarters. Modern purchasing departments couldn't see past the initial price tag. Depreciation schedules ran 10 years, warranty periods covered 3 years, and CFOs changed jobs every 4.2 years on average. No one's career incentives aligned with century-scale thinking. Patterson had built for a time horizon that capitalism no longer recognized as relevant. The market had spoken, and it preferred planned obsolescence to permanent solutions. Dr. Raymond Wu from Carnegie Mellon's Materials Science Department cut his first sample from the Patterson crankshaft with a diamond saw, expecting routine analysis. What he found instead sparked 3 months of investigation that would challenge fundamental assumptions about steel metallurgy. The alloy's microstructure didn't match anything in contemporary databases. It shouldn't have existed in 1906. The required refining techniques weren't invented until 1923. Under scanning electron microscopy, Wu observed grain structures that suggested multiple thermal cycles and controlled cooling rates that demanded precision unavailable in Edwardian-era foundries. Yet the manufacturing date was indisputable, cast into the component itself and verified through archival records. Patterson had somehow achieved metallurgical results that anticipated scientific understanding by decades. The chemical analysis revealed Patterson's empirical genius. His nickel-chromium steel contained trace elements, 0.08% vanadium, 0.12% molybdenum, that modern metallurgy recognized as critical for fatigue resistance but that shouldn't have been intentionally added in 1906. These elements didn't appear in steel specifications until after World War I, when aircraft engine failures drove systematic research into high-performance alloys. Wu's team theorized that Patterson had conducted years of destructive testing, manufacturing components with slight compositional variations, and running them to failure to identify optimal combinations. His notebooks confirmed this approach. Records of 127 different alloy trials between 1896 and 1904, each tested under punishing conditions that simulated decades of operation. Patterson had performed material science research a generation before universities established departments dedicated to the field. The heat treatment protocols proved equally advanced. X-ray diffraction revealed that the crankshaft had undergone controlled atmosphere processing that prevented surface decarburization, a problem that plagued steel heat treatment until vacuum furnaces became available in the 1940s. Patterson's team had achieved similar results using sealed ceramic containers filled with charcoal, reducing atmospheres that protected surface chemistry during thermal processing. The technique was described in obscure German metallurgical journals from 1898, suggesting Patterson had connections to European research networks that most American manufacturers ignored. But the most significant discovery came from fatigue testing of samples extracted from the crankshaft. Despite 118 years of cyclic loading at 180 RPM, over 1.03 billion stress cycles, the material showed no crack initiation or propagation. Modern fatigue models predicted failure between 400 and 600 million cycles for similar stress amplitudes. Patterson's steel had exceeded theoretical limits by 7%, suggesting his metallurgical understanding had captured factors that contemporary science still struggled to quantify. Chen compiled Wu's findings with growing recognition that Patterson represented a lost branch of engineering evolution, one that prioritized empirical excellence over theoretical understanding, results over publications, permanence over patents. His machine survived because he'd solved problems through relentless testing rather than mathematical modeling, achieving practical solutions that formal science wouldn't explain for generations. Chen arranged a demonstration that she knew would anger half the engineering community and vindicate the other half. She invited representatives from 3 major industrial equipment manufacturers to witness comparison testing between the 1906 Patterson machine and their current production models. The manufacturers arrived skeptical, armed with specification sheets that demonstrated their equipment's superiority in every measurable category: power density, efficiency ratings, control precision, and digital monitoring capabilities. The test protocol was brutally simple. Run all machines continuously for 90 days under identical load conditions while measuring performance degradation, maintenance requirements, and total operating costs. The modern machines featured variable frequency drives, PLC controls, condition monitoring sensors, and predictive maintenance algorithms. The Patterson machine featured a flywheel, some bearings, and 118 years of operational history. 30 days into testing, the first modern machine developed controller faults that required a technician with laptop diagnostics to resolve. 60 days in, the second machine needed seal replacements on its electronically controlled lubrication system, parts that required overnight shipping from Germany. The third machine operated flawlessly until day 73, when a power surge corrupted its firmware, requiring complete reprogramming and recalibration that consumed 16 hours of specialist labor. The Patterson machine ran without incident, its only requirement being weekly visual inspection of oil levels that took 30 seconds. When Chen published preliminary results, the manufacturer's legal teams requested the testing be discontinued, citing concerns about Ma-representative operating conditions and inappropriate comparison methodology. Chen declined. The test continued. The financial analysis proved even more devastating. The modern machines delivered 12% better thermodynamic efficiency, compressing slightly more air per kilowatt consumed, but required $43,000 in combined service costs during 90 days of operation. The Patterson machine's electrical consumption was higher, costing an additional $180 over the test period, but required zero service intervention. Total operating cost difference. The modern machines cost 238 times more to operate when all factors were included, but Chen's most pointed critique came during her presentation to the National Academy of Engineering. "We've confused complexity with capability," she argued, displaying vibration spectra from all machines. The Patterson machine achieves smooth operation through fundamental physics, mass, geometry, precision manufacturing. Our modern equipment achieves similar results through electronic compensation for inferior mechanical design. We've replaced craftsmanship with code and called it progress. The industry response was predictable. Trade publications criticized Chen's methodology, her sample size, her failure to account for modern machines' advanced capabilities. Equipment manufacturers issued press releases emphasizing their products' digital features, connectivity, and integration with Industry 4.0 protocols. Everyone carefully avoided mentioning that the 118-year-old machine had outperformed their latest designs in the only metric that ultimately mattered: reliable service delivery over time. Torres watched the controversy unfold with dark amusement. The machine continued running in the Bethlehem basement, indifferent to academic debates about its impossibility. 6 months after the discovery, Chen stood in the basement with a documentary crew filming what might be the machine's final days. The building's demolition was scheduled for August 2025. She had fought to preserve the machine, proposed moving it to MIT's museum, offered to fund the relocation herself. But ownership disputes between creditors, historical societies, and municipal authorities had paralyzed any preservation efforts. The machine would likely be scrapped, along with the building, its brass and steel worth perhaps $8 at current commodity prices. "The tragedy isn't losing this particular machine," Chen told the camera, her hand resting on the warm cast-iron frame. "It's that we've lost the knowledge system that created it. And Patterson didn't just build durable equipment, he built a complete philosophy about humanity's relationship with tools and time. He believed machines should serve multiple generations, that quality meant responsibility to people you'd never meet, that engineering was ultimately about stewardship, not just functionality." The documentary director asked the obvious question: couldn't modern manufacturers simply copy Patterson's approach? Chen's laugh was bitter. "They could, but they won't, because Patterson's philosophy is incompatible with quarterly earnings reports, planned obsolescence, and vendor lock-in through proprietary components. The economic system that emerged after Patterson's death actively punishes the approach that made his machines immortal." She pulled up data on her tablet showing industrial equipment life cycles. Average service life of manufacturing equipment had declined from 43 years in 1950 to 11 years in 2025. Maintenance costs as a percentage of purchase price had increased from 14% to 67% over the same period. The cost of industrial downtime had exploded exponentially as supply chains grew more complex and just-in-time manufacturing eliminated backup capacity. Industry had optimized for everything except longevity, yet the solution stood humming steadily at 180 RPM, demonstrating principles that every engineer understood but no company implemented. Heavy construction absorbed vibration. Generous tolerances accommodated wear without performance degradation. Gravity-fed lubrication eliminated dependence on active systems. Hand-fitted components created mechanical relationships that exceeded specification sheet precision. None of this was impossible. It was simply unprofitable in a system that measured success by replacement rates rather than surface lifespans. Torres arrived with news that the demolition schedule had been moved up. The machine would stop in 6 days. Chen nodded, having expected this outcome. She had documented everything. measurements, metallurgy, manufacturing techniques, design, philosophy. The knowledge wouldn't be lost, just ignored. Future engineers might rediscover Patterson's principles when resource scarcity or environmental concerns finally made planned obsolescence untenable. But that day hadn't arrived yet. The machine continued its rhythm, each stroke identical to the 1.03 billion that preceded it, running toward a finish line that had never been part of its design. But why do we keep building machines that we know will fail, when we've already proven we can build machines that never stop?